Excellent, thank you. It's my great pleasure to introduce our next speaker for this morning. It's Daniel Panazzolo, who will speak, you can see it, on some aspects of resolution of singularities for differential operators. Please.
Okay, thank you. So, so the organizers asked me to give you some overview of the subjects that I intend to cover in this mini course on February. So I will not be very long, so I'll not be able to, of course, to get into too much detail, but I would like just to give some motivation for this problem of resolution of singularities, and most particularly in the case where you consider, let's say, differential operators or some kind of differential structure defined on a manifold. So let me just say in a very general sense, the basic idea is that you have some pair given by a manifold, and I call S some object which is defined on this manifold, which, let's say, is attached to some differential geometric structure on M. And we would like to understand this pair given by the manifold and this additional structure defined on it. Okay, so the basic idea is that you suppose that the local structure of defined by such object S is real, let's say, reasonable, well understood almost everywhere. By this I mean outside some subset of codimension greater than 1 in some well-defined topology. And so we call this set where the things are not so good, the bad locus, right? So the goal of this game is to try to change the ambient pair, let's say the manifold and this object S, by a sequence of proper morphisms, most particularly given by blowups, such that, let's say, basically two conditions must be satisfied. We intend that the composition of all these morphisms gives an isomorphism outside the bad locus. And then we expect that this, let's say, this last pair doesn't have a bad locus. So, of course, we'd like to eliminate all the bad points by this procedure. And in the same way, the first condition asks that in some sense that the structure is preserved outside this bad locus, because it doesn't want to touch the points which are already good in some sense. Okay, so I'm going to give some examples. So of course the zero example is the case where you have some manifold, compact manifold, let's say, equipped with a codimension 1 analytic subset. So in this case, let's say the tradition says that we have to call the bad locus the points where S is not normal crossing, is not local normal crossings. So by this, of course, I mean that locally you are not able to find some coordinates where S is given by the zero of a monomial. And the elimination of the bad locus is the very well-known theorem of Hiranakas on the resolution of singularities, which says that up to a finite number of blowups, you always arrive in this kind of local situation. Well, I just recall that a blowup is this transformation that I've just illustrated here, where, roughly speaking, you separate the orbits of this torus action, whose let's say the orbits are the lines through the origin, and then you just separate these orbits by replacing the origin by a projective line. And more generally, you can imagine this drawing generalizes in a higher dimension, right? So this is the basic tool for that we'd like to use to eliminate this bad locus. And let me just give a very quick example here. So you have this cuspidal curve in P2, and let's say this blue line represents the projective line. So we call this the exceptional divisor that is going to be formed by this sequence of blowups. So so the union of the black line and the blue line corresponds to the transform of the original curve by these maps. So you see that in order to have a normal crossing, you don't have to have more than two local components crossing on a point. So this is achieved by 3 blowups. So you see that after making 3 blowups, you achieve the situation where at each point you have a normal crossing situation. And well, this is just a simple example. So I would like just to recall that there's a basic mechanism of control to show, let's say, the basic is that to show that at each step something is improved by this procedure. So of course, the basic idea is to use some kind of a generalized version of the Newton polyhedron. Now there's more or less, let's say the Newton polyhedron is the basic construction, which is have much more sophisticated versions right now, but basically you expand your function in Taylor series, and then you just consider the integers, the n upples of integers k such that the coefficient ak is non-zero. Then you plot them in the, let's say, in the n space, and you have this. You take the convex envelope, and you have this drawing here. And once you have this, you can somehow measure how bad a singularity is by. So the idea is that you have to measure somehow the distance between the Newton polyhedron and the origin. So, for instance, the classical way to see this is that you take just the L1 distance between the polyhedron and the origin. So this L1 distance is just the multiplicity, right? So the idea is that you want to decrease this distance by making blowups, and once this let's say this nearest point achieves the origin, you won your game. Okay. So the multiplicity is this. So this distance is let's say the basic invariant, but it's not. Of course, it's not enough to define your algorithm. But it has two very let's say good properties. It's horizontal and vertical invariant, by which I mean that it's invariant by local change of coordinates. So recall that to define the Newton polygon, we need to fix some system of coordinates. But once you consider the action of the local system, let's say changes of coordinates on this polygon, it's very easy to see that this distance remains the same. And also is a vertical invariant in the sense that it's invariant by blowing ups. By this, I mean the total transform, not the strict transform. Okay, so now let me just explain some other examples. So you can consider the case of codimension 1 singular foliations. So this is the case where I have a pair given by a manifold and a foliation F, which is locally defined by the vanish. Let's say it's by the integration of a field of hyperplanes determined by the vanishing logs of some analytic one form, like this one, satisfying the integrability condition. So generically, as I said, the leaves are locally immersed as submanifolds of codimension 1. And we can say that the singular set is precisely the set where this local, let's say the leaves are not of the expected dimension. And inside the singular set, there are some, let's say, well-behaved singularities, but there is which you call the elementary singularities, which are defined by some algebraic condition on the one jets, and there is the complementary of this, which you call the bad or the non-elementary singularities, right? So in this case, the idea is to try to eliminate these non-elementary singularities by blowing ups, and this is one of the, let's say, an old result in dimension 2 due to Bendixson and Seidenberg, which has been generalized to dimension 3 by Felipe Cano in the 2005. So I just give an example here, where in the very simple case where, let's say, your foliation is given by the level sets of some function. So I use the same example as before, the cuspidal curve. But now you just give the foliation is defined by the level sets of the function y squared minus x to the power 3. And so you see that here you have this singular leaf which is given by the cusp, and the nearby leaves are just let's say regular ones. But so this is an interesting case because the resolution of singularities of the cusp gives you also the resolution of singularities of the foliation, right? It's not always the case, even if you have let's say a singular leaf like this. But in this case, you see that the locally at each one of these points, you have this this form which defines your foliation. It's given by a monomial one, right? So a nice example of application of this result is the so-called Separatics theorem of Camacho-Sad, which says the following, which says that if you have a germ of singularity of a foliation in dimension 2, and in the complex domain, so there always exists an invariant analytic curve through the singularity, right? It's not true in the real setting. Think of the case of a singularity of center type. But if you complexify this center type singularity, you will find a separatrix through the origin, an invariant curve through the origin and in the complex domain. So this result it makes a strong use of the resolution of singularities in dimension 2, and an argument using some index of in the spirit of the Poincaré-Hopf index theorem. So now I give a third example, which is the case where also you have a foliated manifold, but now the foliation is given by curves, right? So the generic leaves are of dimension 1 instead of codimension 1. And this foliation is locally defined by the solution curves of some analytic vector field like this, right? And okay, so how you can think of this expression as a derivation in the local rings at each point of our manifold. So this is an operator which acts on the, let's say, on the maximal ideal of each point, and a point is singular for this foliation if this derivation maps the maximal ideal into itself, which is completely equivalent to say that there's A1, etc. AN are functions which vanish on P. So using this characterization, we can also define what you call an elementary point. So a point which is singular will be called elementary if when you consider the induced endomorphism in this vector space, so the quotient of the maximal idea by its square. So this endomorphism should be non-nilpotent. Okay, so this is let's say in down-to-earth terms, this simply means that the Jacobian matrix of the coefficients with respect to the coordinates should be a matrix which at least one non-zero eigenvalue when computed at P. Okay, so this is we call this elementary, but of course we could also ask the question, is it true that we understand very well what happens near an elementary singularity? And the answer is, let's say, more or less yes in dimension 2, but there is a lot of things which is left to understand even in low dimensions. But anyway, the philosophy is that we would like to achieve this kind of situation by blowing ups in which all singularities should be of this type, right? So I just give you a small list of topological models that you have in dimension 2.
Daniel, may I ask a question? Jean-Philippe, in your previous slide, so you are working in a complex setting. I mean, this manifold, for example, is a complex manifold.
It could be real also.
Okay, so both. Okay.
Yes.
Thank you.
So this is a small list of topological models that you have in dimension 2. So these are precisely the phase portraits that we get near by an elementary singularity. So you see there's this focus center node and let's say a nice example of application of this resolution of singularities result is that you have a topological classification of germs of real analytic vector fields in the plane near arbitrarily degenerated singularities. So if you consider a non-elementary singularity, you can, by up to a sequence of blowups, you can achieve one of these elementary situations. And when you go back to your original, let's say, ambient space, you get this decomposition in two sectors, in finite number of sectors, which will be of one of these three different types. Right. Okay, so I have to mention also that this, of course, this resolution of singularities in dimension 2 plays an important role in the solution of Dulac's problem, which will be one of the themes of this semester, because it's let's say an initial simplifying step, which allows to, let's say, you take an arbitrary vector field, analytic vector field, and then up to a finite number of blowups, you achieve one of these models, and then you have to understand these models by the machinery of normal form theory, quasi-analyticity, and resummation theory, and so on. Right. So you have this initial simplification, which leads you to the simplest possible singularities that you can achieve by blowing ups, and then you have to use the analytic, let's say, the hard analysis tools. Yeah. So what happens if you try to do this resolution of singularities in dimension higher than 3 for vector fields? So there is one new interesting phenomenon, is that the elimination of the bad locus has necessary to use weighted blowups. So this is one of an example which is has been found by Fernando Sanz and Sanchez. And so what's a weighted blowup? It's let's say it's a sort of generalization of the blowup that you have seen a moment ago, where instead of separating the orbits of the torus action, given, let's say, the usual torus action by the multiplying by a number, you have the orbits are given by this monomial curves. Like let's say here I've drawn a set of parabolas through the origin. So when we want to separate these parabolas by transformation, you have what you call a weighted blowup. So you have to imagine this figure in higher dimensions. So since you have to use these weighted blowups, in fact, you have to generalize a little bit your setting, because you find yourself in this more general category of what you call an orbifold, if you are in the complex domain. But in the real domain, you can also work in the category of manifolds with corners. Which I mean that in the end, you have to allow these corners to appear precisely due to the existence of this weighted blowups. So for the results, so the elimination of the bad locus is also known for vector fields in dimension up to 3. So in dimension 2, it's exactly the Seidenberg's Bendixson theorem, and in dimension 3, it's a result by me on 2007, and then generalized in a joint work with McQuillan for the complex set in 2013. So let me just mention a nice application of this result. So there is a theorem of Brunella, which says the following: if you have a vector field in dimension 3, real vector field in dimension 3, then there always exists an invariant curve through the origin. So it's more or less like the Camacho-Sad theorem, but the important thing is that here your invariant curve is not necessarily an analytic curve, right? It's just an invariant curve, which is, let's see, it's just an orbit of your vector, or perhaps a curve of singularities. So the idea is, again, that you have to make some sequence of blowups until you achieve a situation where you see that you are obliged to have a simple singularity containing an invariant curve which comes from outside, right? So the fact that it has to be some such a kind of singularity, which is an elementary singularity, is also due to some argument using the Poincaré-Hoppe's index theorem. So once you get this invariant curve, you can go back and you get this invariant curve for your initial vector field. So this is one of the nice applications. And one second application, well, let's say a program which is based on this resolution of singularities is the Rousseau's program for the finiteness part of the Hilbert's 16th problem. So one of the subjects of this semester also. So what's the idea is that you have now the Hilbert's problem asks for a bound for an uniform mode for the number of limit cycles for vector fields of fixed degree. So of course this you can have quite complicated vector fields in this family. So you think of this as a family of vector fields. Let's say a vector field defined in the product space. Let's say the phase space is two-dimensional, but you have a huge space of dimension, let's say n, given by the parameter space, which is are the coefficients of the polynomials. Well, this vector field on this product space has let's say the nice property of being, it's not arbitrary because it has to be tangent to the fibration given by parameter equals to constant, right? So imagine that you have this this family here, this fibration given by the let's say the planes parameter equals to constant, and on each one of these planes you have a two-dimensional foliation. Let's say a one-dimensional foliation on a one-dimensional plane, right? So the program for Rousseau consists of trying to simplify these singularities by a resolution of singularities in families, right? So here you have two coexisting structures. You have the vector field, and then the fibration, which defines your family structure. And the idea is that you have to desingularize both objects at the same time in order to achieve, let's say, at the end, a situation where you have sufficiently good or simple singularities where you can again apply the machinery of normal form theory, resummation theory, and so on. Okay, so my time is almost over. I just have to talk about this. Well, so I've worked a little bit on this problem, and I have some, let's say, my intuition is that the existence of this family structure doesn't really simplify the problem, by which I mean that it's perhaps as complicated as the case where you treat an arbitrary vector field on this ambient space of dimension n+2. So I'm working right now on this problem of resolution of singularities for vector fields. And in fact, in some sense, it seems to me very natural to look for a generalized framework where you put all these three problems in the same setting. So by which I call the singularities of linear differential operators. So I will not have time to enter into much details, but so now you have a pair given by manifold and let's say an order D differential operator given locally by, let's say, an expansion like this. And so in this framework, you can see that a hypersurface, let's say the Hironaka's framework, can be seen as a differential operator of degree 0 given by, let's say, multiplication by a function. A vector field defined as an homogeneous operator of degree 1. But of course, there are natural examples where we are interested in looking for higher dimension, let's say higher order differential operators. For instance, the Laplacian associated to, let's say, some singular metric on a surface, right? So this is also interesting to look at singularities of metrics. So in a few words, the idea is the same as previously. We want to attach a Newton polyhedron to phi. And then we see that it's not very easy because it's not simply the Newton polygon associated to the coefficients, but you have to take care to be careful with the fact that it's not the same thing as the singularizing these coefficients fk. Okay, you have this differential structure, which is very important to keep track. So I've just finished with a drawing here. So this is a Newton polygon of a differential operator, and the new idea is that you have to measure the distance between the origin and your polygon. This is, as I said, is a measure of the complexity of your singularity. But now you don't use the L1 metric, but you use an L2 distance, which is in fact associated to some inner product that we are going to define in the course. So it's analog to a construction of a Kempf instability theory in GAT. So I explained to you that this approach provides us a resolution of singularities for surface, at least. So arbitrary order differential operators on surfaces can be solved by this method that I'm going to explain. Thank you.
Thanks very much. Are there any maybe perhaps